All right, so we are now in a whole different unit. Now in Unit 4, which looks at atomic structure and nuclear reactivity. And so this first part is definitely going to be something you are more familiar with, and it's going to be kind of a review for today, which might be a breath of fresh air. So we are going to continue to use those math skills, but we're going to be applying it to calculations and skills that we're going to be learning with application to chemistry-based topics. So if you have a minute and you don't have these things, please pause the video and go find them. You definitely need a periodic table. I know some of you have kind of joined this class at different points in time. At one point, I did give you the option to have myself mail out a periodic table to you because you don't have that ability to print. If any of you need a periodic table in terms of a hard copy of one, please feel free to send me an email. Just make sure you give me the correct address, city, zip code that it's going to, so that way I can again get that mailed out to you, and I can gladly do that for you. You may want a calculator. We're just adding and subtracting, so that's up to you on if you want a calculator or not. And then, like I said, the note handout will be useful as well. So we're going to kind of dive right into topic 4.1, which is subatomic structure, reviewing basically the anatomy, so to speak, of the atom and how to count subatomic particles. So this is the text box on the far right of your handout. So overall, just a general summary of the atom, and you saw that through the video with how big is the atom, that first of all, this diagram is very inaccurate. When you look at different models of different science topics, whether it be the cell or the scale of the solar system, it's very hard to represent things on a very large and very small scale. So the thing this does poorly is that it doesn't show the atom as being mainly empty space. Again, like the video stressed, that this electron cloud takes up the volume, most of the volume of the atom, and this proportion scale doesn't really show that with this particular diagram. The other thing it does poorly is it doesn't show the nucleus as kind of an, again, accurate proportion. So the nucleus is this very small central location, but it's also very dense, which is interesting. So when it comes to properties, basically the nucleus gives us mass and the volume comes from the electron cloud. Right now, we're going to say atoms are neutral. That's a lie. Atoms do not always have to be neutral, and we'll explain what can happen with those as we move on. And that's because we have protons and electrons, two of our subatomic particles that give us charge equal to one another. And going back to our idea of matter, we had things like elements, compounds, homogeneous and heterogeneous mixtures. And so again, what that tells us is that all of those foundational place is, again, that they are built of atoms. So going to the left-hand side of your handout now, we're going to talk about the nucleus. So again, like I mentioned already, that this region is very dense. And again, in terms of volume, contributes very little volume, but essentially all the mass. So another way you can think about scale is if you were standing on a pitcher's mound in a baseball stadium with a marble in your hand, the marble itself would represent essentially the nucleus, and the baseball stadium would represent the electron cloud. So overall, we have protons and neutrons, our two subatomic particles that contribute to the nucleus. And so because of that, the overall charge of the nucleus is going to be positive, and this is where the mass of the atom is going to come from. So breaking down the distinguishing characteristics of protons and neutrons, our protons are where positive charge comes from. In terms of scale and size, they are essentially 2,000 times larger than an electron. So I don't bring up the actual mass of a proton in terms of grams because it's so small that it's just not a very fun number to work with. So when we go about talking about mass of the atom, we don't talk about it in terms of grams or kilograms. We talk about it in what's called AMUs, or atomic mass units. So we assign a proton as having one atomic mass unit. Protons also take on a very key responsibility in that is what distinguishes one element from another. So our current periodic table stands at 118 different elements, and that's because there's basically 118 different arrangements of the protons. So that's what makes oxygen different from hydrogen, different from mercury. It's all about the number of protons. And so if you know the atomic number, and I'm going to show you where you find that on the periodic table, you then know how many protons that element has. Neutrons, on the other hand, are the other particle of the nucleus. These are neutral in charge, so that's why the nucleus overall is positively charged, because again, the neutrons are neutral, protons are positive. In terms of size and mass, we essentially say neutrons are equal to protons. And so neutrons are a particle that can vary. Protons, if you want hydrogen to be hydrogen, there's only one option. However, within that, you can have different variety or proportions of neutrons that, again, can still make an element stay the same. And so that starts to get into whether an element is going to be stable or unstable, meaning that it's radioactive. And that's a topic we're going to make our way towards as we work through this unit. So the last region of the periodic, or not of the periodic table, excuse me, but the atom is the electron cloud. And so again, like I've mentioned and in the video, that this is where the volume of the atom comes from, but no mass essentially is contributed from it. This is where electrons are found. And so the overall charge of the electron cloud is negative, and within that we have what's called energy shells. So the model of the atom is one that has evolved with time. And so this model is called a Bohr model, where it's like a solar system style, where the electrons are like planets orbiting around the nucleus or a sun. And so that is a very incorrect way of thinking. But Bohr models do have places where they are an appropriate way to represent where electrons are. As we make our way into our next unit discussing electrons, we are going to see that that model is going to shift and why it needs to shift. And so the thing that's really important is electrons are essentially what drive chemistry, and especially the topics we cover. So after this chapter, we essentially stop talking about protons and neutrons, and we are going to talk only electrons. That's what drives chemistry, like I've said. So the part that's even more important is we don't even care about all of the electrons. We only really care about what's called valence electrons. And those are those outermost electrons for an element. And so those electrons themselves within that cloud, each of them have a negative charge. So again, if we have equal negative charges in the electron cloud with equal protons in the nucleus, that's where we get that neutral charge for the atom. So in terms of scale and size, the electron is significantly smaller than the proton and neutron. And so we essentially say they have a mass of 0. So that's a little bit of a falsehood in that they do have mass, but their mass is so small and so insignificant compared to the proton and neutron. It's just easier to say that they don't contribute mass to the atom. And so, like I said, the ones we really care about are what's called valence electrons. This is what decides if a chemical reaction is going to take place, and also what kind of bonds an element is going to be willing to form. So what the rest of the topic is going to be for today is going through and how to count subatomic particles. So the first thing is we're going to use two numbers called the atomic number and mass number. So the atomic number is what orders our periodic table, and that again is telling us how many protons an element has. And again, each element has its own unique number of protons to give us their own unique identity. On the other side of things, the other thing that tells us a lot of information about the atom is its mass number. So again, mass number, what two things give mass to the atom? Protons and neutrons. So if you add up protons and you add up the number of neutrons, you know the mass. Or you can use that information to work backwards to figure out protons or neutrons. So here is kind of a good little cheat sheet reference table on how to go about finding this information. So your protons are your atomic number. I'm going to show you a periodic table here in a moment and clarify what I've been discussing. Neutrons, those are your mass number minus atomic number, or you can find neutrons by taking mass number again minus protons. Again, atomic number and protons are the same. If you want to know how many electrons an atom has, at this point, we're going to say it's equal to protons. Again, this is going to change, and we'll talk about how you find electrons when that is not a neutral atom. Atomic number, you have two ways of figuring out the atomic number. If I tell you the name or symbol of the element and you have a periodic table, you then have that piece of information. And the last thing is, if you know how many protons an element has, you then know its atomic number. So again, a lot of these things overlap with one another. And then, like I mentioned on the previous side, If you want to know the mass number, you cannot go to your periodic table to find mass number. I know for some of you, your teachers in the past have done that. We're going to talk about why that doesn't work when we start looking at isotopes. So mass number is your protons plus your neutrons. So from here, we have a table. And before we start filling out that table, I'm going to change my screen for you. And I'm going to open up the periodic table that I sent to you, and it's posted in Classroom. The reason why I like this one is this one, it's in my opinion, easy to read. And the other thing is it's the most up-to-date because it goes all the way to element 118, and it has names and symbols, especially for these elements down here that are synthesized in a lab. So in this particular style periodic table, the atomic numbers are what's up here in these upper left-hand corners. It's like a sentence out of a book. So you have hydrogen with 1, jumping over to helium with 2, and then you just keep reading through it like, again, lines out of a book. When you make your way down here, we start to have this deviation, and we'll talk about why in our periodic table unit. But when you get to atomic number 56, and then you have 71, there's this where we have to flow down to this bottom part of the periodic table. So that happens down here. But like I said, it goes all the way up to element 118. And then we have our symbol, we have our name, and then we have our average atomic mass down here at the bottom. And we're going to talk about how that number is calculated in a few upcoming topics. So going back to our PowerPoint, we have counting subatomic particles. So we have our symbol of our element, we have Cl, and so what we want to figure out is how many protons, neutrons, electrons does it have, what is its atomic number, and what's its mass number. So I'm going to type this in and flip between my screens. So the first thing I can see is that I have Cl, and let me split screen. That might just be a little bit easier. So if you remember, the element Cl is chlorine. If you take a look at chlorine, you're going to find that on the right-hand side of your periodic table, so right here. And so in the upper left corner is that number 17. So that is my atomic number. So then I can start figuring out subatomic particles. So when I go about that, I already know my protons then. That's going to be 17. And we're going to assume this is a neutral atom. So we're going to say it has 17 electrons. So then the last piece is how many neutrons does this particular chlorine have? You do that by taking mass number minus atomic number. So 35 minus that 17. And this is going to give you 18 neutrons. For our next row, we have 15 protons and 16 neutrons. So to figure out electrons, we have a neutral atom. So we're going to say that that's equal to protons of 15. Protons are our atomic number. And then to get mass, you add protons and neutrons. So 15 plus 16 gives us 31. The last thing we need to do to figure out our identity is using our atomic number, 15. If we find that, that's right here on, again, the right-hand side. That's the element phosphorus. So we have uppercase P for its symbol. Element C, you use that a lot in biology. You probably recognize that as carbon. When you find carbon on your periodic table, here's the symbol C. In the upper left corner, we find that its atomic number is 6. So we then know protons have to be equal to 6, and so do electrons. So then to get mass, add 8 and 6 to give you 14. Here we have a mass number of 16, and electrons are 8. So that means protons have to be 8, and atomic number is 8. To get neutrons, take mass minus atomic number, we have 8 neutrons. So in this case, all 3 subatomic particles are equal to each other. Because the atomic number is 8, I find that in the upper left corner. We are working with oxygen, which is an uppercase O. Here we have the symbol Ar. Notice that for both chlorine and Ar, argon, that if there's a 2-letter symbol, the first letter is always uppercase. Second letter, if it has one, must be lowercase. That is going to become extremely crucial when we start talking about chemical naming and formulas, because we will then use chemical formulas all of second semester. So very, very good habit to get into right away. Second letter is lowercase. Argon is over here in column 18. It's atomic number 18. So that tells us that. Protons and electrons. So from there, we're just left with one last piece and taking mass minus atomic number. So we have 22 neutrons. So again, the goal from today was figuring out that we had the structure of the atom, and then from there, counting protons, neutrons, electrons. So you have a homework assignment to complete with this. If you have questions, let me know.